All right, let's talk about something that trips up a ton of JavaScript developers: concurrency. How does JavaScript, of all things, handle doing a million things at once? It's a really unique approach, and I think by the end of this, you're going to see it in a completely new and maybe even brilliant light. So let's just dive right in.
So here's the big question, right? The one that feels like a total paradox. We're always told JavaScript is single-threaded, one thread. It can only do one thing at a time. So how in the world are modern web apps so fast? How do they feel so responsive when they're juggling all this complexity? That's the mystery we're going to unravel.
Okay, so to really get JavaScript's whole deal, we first need to talk about how it's different. We're talking about two totally separate worlds of concurrency. On one side, you've got the classic multi-threading you see in languages like C++ or Java. And on the other, you have JavaScript. It's like they're playing two completely different sports.
And you can see that difference right here. Look at the classic model on the left. The main thread spawns other threads, and then it just sits there and waits for them to finish. It's very hands-on. But now look at JavaScript. The main thread isn't a micromanager. It just says, hey, event loop, here's a task, schedule it. It's not about direct control. It's all about orchestration. It kicks things off and trusts the system to handle the rest.
This table, this is where it really clicks. Check out scheduling. In the old world, the operating system is the boss, telling threads when to run. In JavaScript, nope. The event loop is in charge. But the real game changer is this line right here, shared memory. With classic threads, they all dip into the same pool of memory by default. And that's where you get these nightmare scenarios like data races and locks. JavaScript just sidesteps that whole mess. No shared memory, unless you go out of your way to make it happen.
I love this quote because it just nails it. Threads share memory and fight over time. They're literally battling each other for resources. But JS tasks, they share time and avoid memory. It's a completely different philosophy. Instead of fighting, they're cooperating, taking turns on a single timeline and staying in their own lanes. It's just cleaner. It's safer. You know exactly what's going to happen and when.
Okay, so if the main thread can't ever be blocked, that begs a huge question. What do you do with the really heavy CPU grinding work? The answer is workers. This is JavaScript's secret weapon for true parallelism. But here's the catch, and it's a big one. They come with a very specific and kind of challenging rulebook.
Yeah, you've got to get this out of your head. A web worker is not just a thread, not even close. The best way to think about it is like a completely separate, sealed-off JavaScript universe. It has its own engine, its own memory, its own event loop, the whole shebang. It can't see or touch the main thread's world at all. That's why the term actor is so much better. It's a black box that you can only talk to by sending it messages.
And this is where things get interesting and a little weird. Let's say your worker finishes some massive calculation and now needs to send that result to a server. You'd think it could just, send it, right? Nope. In most cases, the worker has to package up its result, send it over to the main thread, and then the main thread is the one that actually makes the network call. So the worker does all this heavy lifting only to get stuck waiting in line behind the main thread. It creates this I/O funnel.
So why? Why on earth would they design it this way? It seems so inefficient. Well, it's a very deliberate choice, and it's all about safety and predictability. Think of the main thread as the guardian of the keys. It holds all the sensitive stuff, cookies, credentials, you name it. By forcing all I/O to go through it, you get a single point of security. And just as importantly, it keeps the UI from going haywire. You don't have a network response suddenly changing something on the screen while the user is in the middle of clicking on it. It keeps everything in order.
So we have this constraint, this funnel. How do we build screaming fast apps anyway? Well, you can't fight the architecture, but you can master it. It all comes down to a really disciplined set of rules for how you treat that main thread. And this is the single biggest mental shift you have to make. The main thread is not a workhorse. It's not where you do the heavy lifting. Its job is to be a ridiculously fast air traffic controller. It just routes messages, points them in the right direction, and gets out of the way. It schedules, it routes, but it absolutely does not do the work itself.
So how fast does this air traffic controller need to be? Well, to keep your app feeling buttery smooth, to hit that magic 60 frames per second, the main thread has a budget. And that budget is 2 milliseconds. That's it. 2. Anything longer and your users start to feel it. That little stutter, that lag, what we call jank. That's the main thread busting its budget.
Staying inside that 2-millisecond window means you have to live by some very strict rules. Rule 1. When you forward a message, you just forward it. Don't look inside, don't change it. It's got to be a constant time O((1) operation. Rule 2. Use transferables like your life depends on it. Instead of slowly copying a giant piece of data, you just instantly transfer ownership from the worker to the main thread. It's like teleportation for data. Rule 3. No await, no promises. The forwarding logic has to be pure, simple, synchronous code. And that brings us back to the mantra we have to burn into our brains. The main thread schedules, it does not participate.
So when you follow all these rules, something amazing happens. You realize this isn't some awkward workaround for JavaScript's quirks. This whole system, this whole architecture, it's actually a proven, high-performance design pattern. And it comes from a place you might not expect, the world of game development.
Yeah, the whole thing is built on a concept called a temporal hierarchy. Fancy words, but a simple idea. It just means you organize everything based on time. You don't group tasks by what they do, you group them by how often they need to run and how fast they need a response. The stuff that happens all the time, like rendering the screen, gets the absolute highest priority and has zero tolerance for delay.
And this is what it looks like in practice for a JS app. At the very top, the king of the castle, is the render loop. It's running constantly, maybe 60 times a second or more. It can never be blocked. A level below that, you've got user interactions, like a mouse click. Important, but not happening every 16 milliseconds. And then way down at the bottom, you have the slow stuff. The messages going back and forth to the server, or some huge update to your app's data. Each level has its own rhythm, its own tolerance for taking a little longer.
And I've got to say it again because this is the key takeaway. This is not a hack. This isn't a clever trick to paper over JavaScript's limitations. This strict separation of concerns, this hierarchy of time, this is exactly how high-performance game engines work. It's how they keep the frame rate silky smooth while a million other things like physics and networking are happening in the background.
And boom, here's the grand finale, the big aha moment. Look at how perfectly this all lines up. The main thread's render loop in JavaScript, that's the game engine's render loop that sends stuff to the GPU. The slow back and forth between our workers and the server, that's the game's simulation and network loop. And our strict 2-millisecond forwarding rule, that's the exact same concept as a game engine firing off a command buffer to the graphics card. It's a tiny, fast, here, you deal with this operation. It's the same pattern. It's a one-to-one match.
So this leaves us with a really interesting thought. Maybe JavaScript's biggest constraint, its single thread, is actually its greatest strength. By forcing us into this hierarchical model, it pushes us to build apps that aren't just fast, but are also safer and way more predictable than the old multi-threaded way. So the question is this the future? Is this the blueprint for how we're going to build the next generation of truly high-performance, complex apps on the web? Something to chew on. Thanks so much for joining me.